Today I will talk on interior penalty function method or web barrier method. This is another technique, indirect method for solving nonlinear programming, constraint programming problem. This is now let us consider again the nonlinear program, that is minimization of f x subject to gj(x) less than is equal to 0. A set of nonlinear constraints are there. Now, this barrier method or the interior penalty function method, here we are considering again the penalty of not getting the optimal solution. We have to bear it and we will try to minimize the penalty function. Now, that is why this kind of methodology we are just converting the constrained nonlinear programming problem into unconstrained nonlinear programming problem. Now, for minimization type of problem, we are considering the penalty function as positive penalty function, because we are trying to minimize the objective function as well as we are trying to minimize the penalty function. Now, in the penalty term there are two components, one is the penalty parameter and another one is the penalty function. Now, we are concerned about the penalty term. In minimization problem, we are minimizing the penalty term, and for the maximization problem, negative of the penalty function we have to maximize, because maximization of objective function does not mean that maximization of the penalty function as well. Penalty is something that is not desirable. We are incurring penalty because the corresponding point, rather the corresponding location of my algorithm, that is not optimal, that is either within the feasible region for the interior penalty function, and for exterior penalty function this point will be outside the feasible region. That is why we can just convert this constraint minimization problem as unconstrained minimization problem as minimization of objective function summation Cj Bj, where Bj is the penalty function. In interior method we call it as a barrier function. Why we are calling it as a barrier function, I will just discuss later on, but this is a penalty function. If the point is not in the optimal or rather the boundary of the feasible region, this barrier functional value will be positive. Now, Cj will be the corresponding penalty parameter. As a whole, we are having a summation of all penalty terms. Now, as many number of constraints we are having, that many number of penalty terms we will have. That is why we will have, this is the unconstrained problem, and this can be solved either through the differential calculus approach by considering the first order necessary condition, second order optimality condition, or we can choose any region elimination technique as well for solving this kind of problem. But using the region elimination technique, you know there are certain restrictions to it, because in the region elimination technique the function must be unimodal, then only. But in this case, once we are having f x as a nonlinear function, that nonlinear function can have different modes, okay, different peak points, minimum peak or maximum peak. We are trying to find out the global minimum or global maximum for the corresponding problem. Similarly, for the function gx, that is also nonlinear. When we are adding these two terms, we are not sure, we cannot expect even always the function will have unimodal within a range of definition. That is why region elimination technique, if you want to apply, then we have to break the intervals into different parts, and in different parts we need to check the unimodality of the function, then only we can use the region elimination technique. But in general, this kind of nonlinear programming problems, the objective function as well as the constraint, these are all continuous in nature. That is why better to use the simple technique we know, that is the differential calculus approach, that is the classical optimization technique, we can adopt it. Okay. Now this we know that for the exterior penalty function method, there is a penalty term and we are naming it as a penalty function, but for interior penalty function method, this is the barrier. Okay, but we are having a sequence of unconstrained optimization problem. That is why this kind of penalty methodologies is being termed as SUMT, that is a sequence of unconstrained minimization technique, and this is for the minimization problem, and if we have the maximization problem, then we will have the sequence of unconstrained maximization technique. This methodology is being named as, termed as. Now there are different penalty function you must have realized in exterior penalty function method. Similarly, here also we are having different kind of barrier function, but the barrier function should have certain property. If we say that we are right, if we just make the unconstrained objective function as fx plus c bx, then we need to know what is the property of bx, what is the property of c, how c and bx are behaving. One thing is clear, that it is the process is moving, we are having a sequence of unconstrained optimization problem, but all the problems are being defined within the feasible region. Okay? That is why the behavior of c and b must be examined for this case, because the behavior will not be same as exterior method. Now, if I want to get the property, if you ask me what is the property of bx, then again I should mention the same, just like your exterior penalty function method, that your barrier function must be positive throughout and barrier function is continuous, since gx is continuous. Bx is the function of gx. That is why bx is continuous, bx is positive, and bx is tending to infinity as x approaches to the boundary of S. S is the feasible region of the. Now, you see, whenever we are writing minimization of fx plus cbx, here we are not considering x within the feasible space. You must have seen that we are considering x is in Rn. Rn we are considering because for the points where the points are outside the feasible space, in that case bx will be 0, but once it is within the feasible space, then bx is positive. Alright, but there is a trend of bx as well, just like your px as you have seen. Now, bx is being something that is being measured as a violation penalty because of violation of constraint. Okay. Now, one barrier function can be considered as 1 by constraint function. If we are having one constraint function gx, then barrier function can be considered as minus 1 by gx. You see, gx is always less than is equal to 0 in general model we are considering. Our model is minimization of fx subject to gx less than is equal to 0. That is why within feasible space gx is always less than is equal to 0, but outside the feasible space gx is greater than equal to 0. But if we consider within the feasible space, we are starting our sequence from the feasible region only. That is why 1 by gx will be always negative, and if we consider minus 1 by gx, then it will be positive. Alright, this is one of the barrier function. This barrier function is being named as termed as the inverse barrier function. There is another kind of barrier function, that is the logarithm barrier function. There we are considering the barrier function as minus log minus gx. that is also gives you Bx as positive, okay, because Gx is negative, that is why. Now, this summation is being considered because this summation gives you the value for all constraints together. We are considering all 1 by Gx for all Gjx. That is why this way we will consider the barrier function. Now, if you remember, I was just explaining one problem, that minimization of fx x greater than equal to 5. Okay? Now, once we are considering fx equal to x as objective function, x greater than equal to 5 as a constraint, then if I just make it in the form of Gx less than is equal to 0, then I will write down it as 5 minus x less than equal to 0. Now, your feasible region is x greater than equal to 5. Now, for x equal to 6, the value will be negative, ultimate 1 by Gx, that is why 5 minus 6, that would be negative, that will be minus 1, and another minus is there for with Bx, that is why it will be the penalty you need to incur, that is 1. For x equal to 7, penalty you need to incur as 1 by 2 in this way. But you see, if we consider, if we are just reaching to the boundary of the feasible region by considering x equal to 5, though x equal to 5 as the optimal solution of the problem, the disadvantage of this methodology is that you will get the unbounded solution, because 1 by x minus 5 when x equal to 5, it will give you infinity. That is why this barrier function has the disadvantage that always it makes a barrier within the feasible space by constructing the unconstrained function. That is why this method is being named as the barrier function method. That is the barrier we are considering within the space. Okay? Now, let us consider these two barrier functions in interior penalty function method. Now, if we again consider there is a sequence of C. Now, we got the impression what should be the case, what should be the property of Bx, that is the barrier function, but we do not know what is the property of C, how C behaves within the feasible space. If I want to move towards the feasible space, not exactly the boundary of the feasible space, at least towards the feasible space, then whether C value will increase or decrease. As we have seen for the interior penalty function method, the value of C is always, if we just increase it, then we will reach to the boundary of the feasible region. But in this case, we will see if we just decrease the value of C, we will reach to the boundary of the feasible region. We will have a feel with certain examples, but for different C, we will get a sequence of unconstrained optimization problems. That is why if we consider k as the index of iteration starting from k equal to 1, then C1 will be considered such a way that we will be within the feasible space. Okay. Now, C2 will be considered, C2 must be lesser than C1. Okay. Then only we can move towards the feasible boundary of the feasible region. That is why in this method, instead of increasing C, we have to decrease C. But there is another convention you will see in the literature, that in the barrier function method, people are not considering the constant term, that is the parameter, barrier parameter Ck as Ck. They consider 1 by Ck. That convention is there. Why it is so? Because to make Ck as similar as the exterior penalty function method. As we are saying that we are trying to decrease Ck, if I make Ck as 1 by Ck, then we can say that we are increasing 1 by Ck. That is why that convention is there. Otherwise, if Ck tending to 0, we will see the barrier function will tend to infinity, because if Gx is equal to 5 minus x less than is equal to 0, then 1 by Gx is 1 by Gx at x equal to 5 is infinity. That is why this barrier function, that is a Px, it is not Px, that is Bx, that Bx will go to infinity if x approaches to the optimal solution. That is the understanding. That is why for this case, if I want to solve the nonlinear optimization problem, then we have to select K C in such a way that we will remain in the feasible space, all right. And this selection is not really so easy. Why? Because this selection, if the C value is very high, then in that case we will be far from the feasible space. What should be the optimal value for C? What is the suitable value for C? That is also a question, because we are assuming certain C value. These are all the disadvantages. There are different methodologies available for nonlinear constraint programming problem, that because of these drawbacks, all right. Now, let us just try to solve the problem, and it has been written, if the constraint is satisfied critically, then the solution is not obtained. The problem will be unbounded, okay. Objective function will be unbounded. That is the. Now, let us consider one problem, minimization of 1 by 1 minus x subject to x less than is equal to 1. Let us consider it. If this, then let me make the unconstrained problem as Ckx is equal to 1 minus x minus Ck, and let me use the logarithm barrier function. Then ln x minus ln minus x minus 1, that means it is 1 minus x, all right, by using the logarithm barrier function. Now, we have to minimize this objective function, where this is the function f x plus c k barrier function, where barrier function is equal to minus ln minus g x, where g x is of the form g x less than is equal to 0. Clear? Now, if I want to minimize, let us consider the first order necessary condition. Then grad of r must be is equal to 0. Now, there is only one variable here, that is why we can see that this is equal to minus 1 minus c k divided by 1 minus x, and because of 1 minus x, this is plus, this is equal to 0, all right. This is the first order condition. If I just take x, then 1 minus x, x minus 1 plus c k is equal to 0. From here we are getting x is equal to 1 minus c k. Clear? That is why let me consider first k is equal to 1. Let consider C1 is equal to some value, point, very high value we will start 995. Okay. Then what will be corresponding optimal solution for this? X star must be 1 minus c k, that is why the x star value will be 0.0005. Okay. Now, I have to increase C1, I have to decrease C1, that is why let me consider C2 as 0.1, then corresponding x star would be is equal to 0.9, all right. If I consider C3 is equal to 0.01, then x star would be is equal to 0.09, C4 is equal to 0.001. X star would be is equal to 0.999. Similarly, C5, what you see the pattern? It is approaching to 1. C6, we can go further. Okay. What we see that if Ck is tending to 0, x star is approaching to 1. That is why we can say x is equal to 1 could be the optimal solution for this problem. This way we can solve this problem. Now, if I say what is the algorithm for solving this interior penalty function method, first of all we have to select a value for C1 for k is equal to 1. The consideration of C1 depends on the feasible point, that is why we will consider a feasible point within the space. Now, let us start the initial feasible point at x1 such that Gj x1 less than 0. Okay. Now, in this case, as it was for exterior penalty function method, that we have to consider one point which is outside the feasible space. How we checked it? We checked it, we were considering a point which was, if there are 3 constraints, we were checking at least one of the constraints should not be satisfied with that point. But in the interior penalty function method, we need to consider that all constraints must be satisfied, then only this is the feasible point. That is why x1 must be feasible point for all j. Now, once we are getting C1j, formulate the unconstrained problem, find the minimum and check for optimality. Check for optimality, the only thing we cannot do, because unless we just proceed. Now, because we are more interested to get the sequence of unconstrained problem, and we will say that you see we are converging as Ck tending to 0, we are converging that sequence, the limit point of the sequence is this one. Okay. Now, that is why we are considering another C that is lesser than the previous C. Then again we are just doing the process and we are getting the solution this way. Let me consider another problem for this. x1 minus 2 x2 subject to 1 plus x1 minus x2 square 0. If this is the problem for us, then we can say that our Ck x must be is equal to x1 minus 2 x2 minus, if I consider gx will be x2 square minus x1 minus 1 less than is equal to 0. Now, this problem we have already solved with the interior penalty function method, exterior penalty function method, and I am just considering this as C 1 by x2 square minus x1 minus 1. Okay. And you solve this problem with the exterior penalty function method by considering delta r is equal to 0. Find out the value for x1 and x2 in terms of C, then you take C tending to 0 and find out the value of it. In this process, one thing I would like to say that you see we are considering r Ck x is equal to f x minus Ck divided by summation g j x, all right. And what is the grad r? Grad r is equal to grad f x plus Ck summation 1 by g j x square into grad of g j x. Okay. Now, you see, look at this term, you recall the Kuhn-Tucker condition. What was one of the condition in the Kuhn-Tucker condition for inequality constraint? That was grad of f x plus Lagrange multiplier grad of g j x, all right. Here also we can say that Ck summation j is equal to 1 to m 1 by gjx whole square tending to lambda star, that is the Lagrange, that is the KKT multiplier as x tending to optimal point. All right. Now, what are the other thing is we can say that lambda star is equal to 0 for active constraint and lambda star not is equal to 0 for inactive constraint. Here also we can say when this lambda star is finite value, then we can say that we are getting that corresponding Gj would be the, this is finite active constraint. All right, this is one consideration. Now, let me take another example for solving with the interior penalty function method. Minimization of x1 square plus x2 square subject to 1 minus x1 minus x2 less than is equal to 0. Consider the barrier function r is equal to x1 square plus x2 square minus c ln minus of these, that is why it will be x1 plus x2 minus 1. All right. Consider the grad of r. Grad of r would be is equal to 2x1. If I just differentiate with respect to x1 this one, then 2x1 minus c divided by x1 plus x2 minus 1. And if I just partially differentiate with respect to x2, this is equal to minus c divided by x1 plus x2 minus 1. This must be is equal to 0, and this gives you the at the optimal stage x1 star must be is equal to x2 star, because if we just equate equal to 0, this is less than is equal to 0, these two terms. From there we can say that x1 star is equal to x2 star. Not only that, we can say that this is equal to 2 plus 2 root over 1 plus 4c divided by 8 plus minus, because we will get the condition like this. Okay, if we just substitute x1 is equal to x2 here, then we will get this equation with of degree 2. From there we will get 2 roots of the equation. Now, one point, that is if we just substitute the values here, we will see that 2 minus 2 root over 1 plus 4c divided by 8 is not within the feasible space. That is why only the point we have that is in the feasible space 2 root over 1 plus 4c divided by 8, this is in the feasible space. Now, one thing you can do by changing the value of c, you will get a sequence of optimal solutions, because we know x1 star is equal to x2 star. We can have for different values of c starting from say 0.9, 0.8, 0.7, x1 we can have, x2 we can have functional value, the r we can have the functional value as well. We can have a table like this. Okay, we will get by substituting the value of c 0.9, we will get 1 plus 4 into 0.9 root of that, 2 into this, etc. Then that would be the value for x1, same is the value for x2. We can complete this table. This is one way of getting. Okay, and we will see that where x1, x2 values are converging and the corresponding r value will converge or f will converge, that would be the solution. Okay. Other way, what we can do, we can take c tending to 0. If c tending to 0, what we see that x1 value will tend to 2 plus 2 divided by 8, that means half. x2 value is tending to half. That is why we can declare half is the optimal solution. Okay. Same thing you will get through this table as well. What I suggest, you just check it. And for the previous problem also, just do the same exercise for that problem also. Thank you for today.